We're going to shift gears a little bit today from the study of the electron, the discovery of the electron, the measurement of the charge of the electron, that thing that we now know orbits around the nucleus. We're going to shift from that to the study of the nucleus itself, to a phenomenon called the radioactivity. Radioactivity, you've all heard of it. You might not know what it is. Radioactivity is a natural process. First of all, it's a natural process. It's a random process. What does that mean? Well, it means that it happens on its own. We don't control it. We don't make it happen. We don't decide when it happens. We don't control when it happens. It is completely natural, and it is completely random. Now, that just still doesn't say what it is. It just says that we can't control it. It is a natural process. It is a random process in which a nucleus of an atom, and you know that the nucleus of an atom, you know this from Science 10 and from Chemistry 20, you know that the nucleus of an atom consists of protons and neutrons, not electrons, where one nucleus decays into something else. So carbon is no longer carbon, or nitrogen is no longer nitrogen, or uranium is no longer uranium. The nucleus itself changes into something else. We have a nuclear reaction here. In chemistry, you're learning about chemical reactions, things involving the electrons that orbit around the nucleus, the interaction of electrons that cause certain elements to interact with other elements. Now we're talking about interactions between protons and neutrons in the nucleus itself, and changing not one compound to another compound, but one element to another element. The resulting radiation that is produced here is not, well, I shouldn't say, I was going to say is not electromagnetic radiation. One type of it is actually electromagnetic radiation, but the other types aren't. But they are, just like X-rays and gamma rays, ionizing radiation. That means that when we have this radiation that's produced as a result of radioactivity, that radiation can ionize atoms, can turn atoms into ions. That's why radiation can be so dangerous, because it can turn atoms into ions, and when you have ions, they react chemically different than just atoms, and strange things start to happen. If you have ionizing radiation inside your body, and it causes atoms inside your body to become ions, and you start getting these chemical reactions inside your body that aren't supposed to take place inside your body, then it can lead to all kinds of crazy things, including radiation poisoning, certain types of cancers, cataracts in the eyes, reproductive issues, all kinds of issues that result from these chemical reactions taking place from these ions that aren't supposed to be in there. So it is a natural process. We don't make it happen. It is a random process. We don't control when it happens. It's just a natural random process whereby a nucleus changes into something else. And as it does that, it produces radiation that is ionizing, that turns atoms into ions, which sometimes is a bad thing. Sometimes can be a good thing too, but oftentimes is a bad thing. Now, this is a big table. Bear with me on this one. There's 4 types of radioactivity that we talk about in Physics 30. The first type is called alpha decay. Where have you heard that word before? Alpha. In the context of physics, that is. Sorry? Well, it is a letter in the Greek alphabet, yeah. That's the first letter in the Greek alphabet. An alpha particle, yeah. You've used alpha particles before. You've used them in problems before, but you haven't really known what they are. Alpha decay is what makes these alpha particles. So for the first time today, you're going to learn what an alpha particle actually is. Alpha decay occurs when you've got a nucleus that's pretty big and is unstable. And as it tries to become more stable, as it tries to become more, what's another word? More stable. I can't think of another word for it. The nucleus is unstable because of whatever reason. As it tries to become more stable, it gives off an alpha particle. And as it gives off that alpha particle, it changes into a new nucleus. That alpha particle that it gives off has a symbol that looks like this. Now, if you're in chemistry, you'll know what these numbers mean. This is what we call isotope notation. The bottom number is the number of protons. The number of protons, sometimes we call it the atomic number. So an alpha particle actually consists of 2 protons. The top number is what we call the nucleon number. It's the number of nucleons, the number of protons and neutrons. So we have 2 protons and we have 4 protons and neutrons. So an alpha particle would consist of 2 protons, and 4 minus 2 is two neutrons. That's what an alpha particle is. You get this big nucleus that's unstable for whatever reason, and it gives off this alpha particle in an attempt to become more stable. All this alpha particle is two protons and two neutrons, which, by the way, is chemically identical to a helium nucleus. In fact, we sometimes write an alpha particle symbol not as 4,2 alpha, but as 4,2 helium, because it's exactly the same thing. Exactly the same thing. Yep. Yes, please. Yeah. Now, I want you to understand here, this is ionizing radiation. Like this is potentially very, very harmful to us. This could cause cancer and all kinds of other things, like alpha particles. Does that mean that since alpha particles are the same thing as helium nuclei, when we breathe in helium, that we're breathing in these things that are very, very bad for us, that can cause all these chemical reactions and give us cancer? No. How many people have ever done that? How many people cut the end off of the balloon and breathed in helium? Yeah. I missed a day of school last year because my son, who was 9 years old at the time, it was his birthday like a couple weeks before. He had helium balloons in his room, and he decided one morning before school to cut off the end of the helium balloon and breathe it in. So he does that, and he calls his mom and me in to listen to him. And just as we get in there, he breathes it in. He starts talking, and then he passes out and falls flat on his face, passes out. Did he pass out because he has all this ionizing radiation in his body now that causes all this damage? No, not at all. He filled his lungs with helium, and when you fill your lungs with helium, there's no oxygen in them. So what happens? You pass out. Once you can breathe oxygen again, you're fine. Now, I wouldn't suggest doing that on a regular basis, but it's not going to kill you, generally at least. It is conceivable, but not likely that it's going to kill you. But if it does do damage to you, it's not because of radioactivity. He breathed in not helium nuclei or alpha particles, he breathed in helium atoms. So not just the nucleus, but the nucleus with two electrons orbiting around the nucleus as well. And that makes all the difference in the world, a helium atom versus a helium nucleus. All right. Now, this is two protons, two neutrons. So this is matter. Helium is matter. Alpha particles are matter, not energy, it's matter. Just like your desk is matter. The alpha particles are just a lot smaller, that's all, and a lot lighter. Now, beta decay, it occurs when a nucleus is unstable for a different reason. We won't go into the reasons, the specific reasons why each of these types of radioactivity occur. Okay, just know that beta decay occurs for a different reason. It tends to occur in smaller nuclei. The nucleus decays in an attempt to become more stable. And what does it become? What does it give off to become more stable? It gives off this thing, a beta particle. That's the second letter of the Greek alphabet. That's the same thing as what? -1? Oh, wait a second. We said that bottom number is the number of protons. -1 protons? Well, it's actually not really the number of protons. It's actually the charge, which usually is the number of protons. A -1 would correspond to an electron. Look at the top number, the nucleon number. There's 0 protons and neutrons. 0 protons and neutrons. There's -1 for a charge. So that must mean that this is the same thing as an electron. And it's weird that you can get an electron out of the nucleus when there are no electrons in the nucleus, but it's really weird, actually. You don't need to know this, but the nucleus is unstable for one reason or another. It's an energy thing. And in an attempt to become more stable, it actually changes a neutron into a proton and an electron. So you've got a neutron that disappears and becomes a proton and an electron. And the electron gets kicked out because it doesn't belong in the nucleus. And that electron is the beta particle. It's exactly the same thing as an orbital electron. Exactly the same thing as an orbital electron. Just where it comes from. So that's sometimes why we distinguish it and call it a beta particle. This is also matter because electrons have mass. Sorry, you know what? Change this. I should have made this beta negative on the top. and beta positive down here. I just reversed those, sorry. When beta positive decay occurs, the nucleus is unstable. In an attempt to become more stable, it releases this, 0 plus 1 beta, a beta positive particle, or beta plus, which is exactly the same thing as a, look at the top number, the nucleon number. How many protons and neutrons? 0. 0 protons, 0 neutrons. Plus 1. Wait a sec, the charge is plus 1, but there's no protons? Well, it's not an electron. It's not a proton. It's not a neutron. This is what we call 0 plus 1e. That's a positron. You ever heard of a positron before? A positron is not energy. But guess what? It's also not matter. A positron is what we call antimatter. Have you ever heard of antimatter? Antimatter is exactly the same as matter, except for one property. Usually, it's charge. So a positron is identical to an electron, except for the charge. It has the same mass, same property, same spin, everything, except for the charge. It's positive. When a positron and an electron come together, they annihilate and become pure energy. So the matter disappears and becomes pure energy. Anybody ever read the book Angels and Demons? Or saw the movie Angels and Demons? No? Not so realistic, but pretty entertaining, actually. There was this antimatter bomb built. The idea of this antimatter bomb, and technically, if we could build one of these things, we can't. It's technologically not possible right now. But if we technically could build one of these things, it would be far, far, far more powerful than a nuclear bomb, because in an antimatter bomb, we'd be taking all the matter and antimatter, and it would be completely obliterated. It would be completely converted into energy, which would be much, much more powerful. But the good news is we can't do that. Not yet, at least. So what is this, matter, energy? No, it's neither one. It's what we call antimatter. And finally, the last one that we do is called gamma decay. Gamma, where have we heard that word before? Gamma rays? Yeah, gamma rays. Here's a symbol for gamma. 0, 0. That's the Greek letter gamma, kind of. How many protons? Zip. How many neutrons? None. How many electrons? None. How many positrons? None. What is this? This is energy. This is energy in the form of EMR. Remember in the last unit, on the very first day, we went through the EMR spectrum. Gamma rays are on the last, the seventh and final type of EMR. Do you remember how we said they were produced? We said that gamma rays are produced by nuclear decay, radioactive decay, when matter is converted to energy. This is the same gamma ray that we were talking about the last unit. We're just talking a little bit more about how it's made and the properties of it. So remember, you got this nucleus, uranium, let's say, uranium-238, and it's unstable for whatever reason, and it decays in an attempt to become more stable. As it does that, it gives off one of these types of radiation. Now, that doesn't mean the uranium is completely gone. It's not. There's still a big nucleus there. It's just not uranium anymore. Because if it's given off, let's say, an alpha particle, then it's lost 2 protons and 2 neutrons, and therefore changed into something else. So it's still there, but it's just not uranium anymore. You've given off, let's say, an alpha particle, and now you're left with this other element that may still be radioactive, or may not be radioactive. Okay? But it's closer, at least, to becoming stable. All right, now let's look at 2 properties of each of these types of ionizing radiation. One, the penetrating power. What do you think I mean by that, the penetrating power? What does that mean? Go ahead. Kind of. What it will go through, what it will penetrate, what it will go through. Will it go through a piece of paper? Will it go through the wall? Will it go through a thick concrete wall, the ability to penetrate matter. Here's the good news. Alpha particles have a very, very low penetrating power. About a sheet of paper. So you guys have that opportunity on your final assessment to replace your mark. It's your class mark or it's your final assessment mark, whichever one's higher. I hope you do better on that. There's a chance you will do better on it. If you work hard preparing for that, there's a chance you'll do better on it and improve your mark. I hope you do. Some of you will. Some of you won't. Hypothetically, somebody who doesn't improve their mark gets mad, says, oh, I so wanted to improve my mark on that. They get mad and they come and talk to me and they start yelling at me. And then they say, you know what? Oh, I'm so tempted to pull out my alpha particle gun and zap you with it. You know what I would say to that? You know what I would say to that if you threatened to zap me with your alpha particle gun? I would say, bring it on. That's what I would say. You know why? Because I have my alpha particle shield right here in my hand. This is my alpha particle shield. If you pull out your alpha particle zapper gun and threaten to shoot me, I'm just going to hold up my shield and shield myself from the alpha particles with a half a dozen sheets of paper. The penetrating power of alpha particles is very, very low. It might go through a piece of paper. It's not going to go through a stack of paper like this. It's very low. So that's the good news. It's ionizing radiation. It can do quite a bit of damage, but it doesn't go through very much. So it's not going to penetrate into our bodies. Beta particles, whether we're talking about beta negative or beta positive, they're kind of like, well, it's not huge penetrating power, but it's more than alpha particles. We would say it's about 1 to 2 centimeters of flesh. So you might burn me with your beta particle zapper, but it's still not going to penetrate into internal organs. But it will go through my skin, unlike alpha particles. Gamma rays, on the other hand, man, their penetrating power is very, very high. We'll say several centimeters of lead. Gamma rays are, by the way, what's used in radiation therapy for cancer treatment. Sadly, all of us probably know somebody who's had cancer treatment with radiation therapy. When that happens, they don't actually zap you with a gamma ray beam. They zap you with several gamma ray beams from different directions. And they do that because, well, gamma rays are ionizing radiation. They cause damage to cells. So if you have a tumor somewhere in your body and they zap it with a gamma ray, well, it's not only going to do damage to the cancer cells, it's going to do damage to the healthy cells as well, to the good cells. So as it goes through the good cells to get to the cancer, it does damage to both of them. So what they do is, pretty ingenious actually, they map out the tumor. They know exactly where it is in your body. And then they zap you from this direction, and this direction, and this direction, and this direction, all these different directions, so that all these beams do a little bit of damage to have the healthy cells, but where they all intersect is where the tumor is, and they do a lot of damage to the cells there. Does that make sense? But these gamma rays have such a high penetrating power, they easily go through our bodies, cause damage to healthy cells, and particularly the cancer cells. They would easily go through these walls. So a cancer treatment room where they give radiation therapy, the walls are made of concrete, and not just like 4 inches of concrete, but several feet of concrete. Like we're talking like a meter or more of concrete. The walls and the ceiling are that thick, made out of concrete, to shield the outside from these gamma rays. You wouldn't need to do that for alpha particles, but you do for gamma rays because they penetrate so much. Now, on the flip side of all that, what about their ability to ionize matter, to ionize atoms, to turn atoms into ions that will do silly things that they're not supposed to do? Right? That's why gamma rays can cure cancer, right? Because you zap these cancer cells with gamma rays, it ionizes atoms, turns them into ions, chemical reactions start taking place, and the cancer cells die. So do healthy cells, though. But if you zap healthy cells with just a little bit of gamma ray, it's probably going to be okay. If you zap the gamma rays with a lot of, or sorry, you zap the cancer cells with a lot of gamma rays, then they're going to kill the cancer cells. How much potential do these particles have to ionize matter? Well, the good news was that alpha particles have a very low penetrating power. The bad news is they have a very high ability to ionize matter. So they have a hard time getting in your body, but if they're in your body, watch out. Gamma rays have a very high penetrating power, but they have the lowest of the three ability to ionize matter. I don't want to say low or especially very low, because like it's significant, their ability to ionize matter, but it's the lowest of the three. And then here's our beta particles, again, our fence sitters, which they were in the middle of penetrating power. They're in the middle of ionizing power as well. When you have a radioactive particle, you do need to worry about, if you're exposed to radioactivity, you do need to worry about gamma rays that are produced. But unless you consume the radioactive particle, you likely don't have to worry about alpha and beta. Think about that. Here's the radioactive material sitting on that desk right now. It produces alpha particles. I don't need to worry about that because I'm shielded by my clothes from alpha particles. I probably don't need to worry about this one either that produces beta particles because they're not going to penetrate into my body. They penetrate like a centimeter or so of flesh. They'll burn my skin, but they're not going to penetrate into my body and give me lung cancer, right? The gamma rays that maybe they produce, like they can penetrate into my body and cause damage, but the alpha and beta won't. For alpha and beta to be concerning, we generally have to consume the radioactive material. Consume it. What do you do? What do you eat? Radioactive material? Who eats radioactive material? Well, all of us do. All of us do. Eat bananas? Yeah, well, bananas are radioactive. Did you know that? They are. Not a high degree of radioactivity, but they are radioactive. So is everything else. Just about everything else contains carbon, right? And there's a certain proportion of carbon, of naturally occurring carbon, that is radioactive carbon-14. So every time we eat something, every time we breathe, we're breathing in radioactive material. It's just that our bodies repair itself. Our bodies repair themselves quicker than the damage is done, unless we're exposed to a lot of radioactivity. Does that make sense? Now, let's finish off class with just a little bit of information about what the nucleus looks like after this has taken place. Let's talk about something called transmutation. Transmutation is the conversion of one element to another. Doesn't that sound a lot like the definition we gave for radioactivity? Radioactivity is one way in which transmutation can occur. Transmutation is the conversion of uranium to whatever. Radioactivity is one way in which that can happen. It's a natural, spontaneous, random process in which that can happen. There are other ways that transmutation can take place as well, other ways that we can change one element to another as well. Radioactivity is one of them. The conversion of one element to another. It can happen among other mechanisms by radioactivity. We're also going to talk tomorrow and then actually the next day, I guess Thursday, about another couple of ways in which transmutation can happen as well. Nuclear fission, nuclear fusion. You may have heard about those before. What we're going to do here now is look at what we call a transmutation equation, which is an equation that describes the reaction. In other words, what ends up being produced. It's similar in a way to chemical equations, right? When you balance chemical equations. But the good news is it's easier. It's a lot easier, actually, than balancing chemical equations. But they describe a nuclear reaction in a similar way that a chemical equation describes a chemical reaction. To write the nuclear equation, we want to make sure the mass numbers, I'm going to change that name actually, the nucleon numbers. The nucleon numbers, that's the number of protons and neutrons, that's the top number. And the atomic numbers, that's the number on the bottom, are going to balance. So make sure the top number and the bottom number in that isotope notation balance each other. Okay, let's take a look at one example here. There's a couple of few that we want to do here, but let's take a look at the first one. These go pretty quickly for us, guys. You're going to have a worksheet to do in a few minutes. It's going to look big, lots of questions on it, but each question takes maybe 15 seconds, 20 seconds to do. So it's really not that bad at all. This one says, write the nuclear equation for the transmutation of radioactive isotope radium-226 undergoing alpha decay. So this is radium-226. Let's write that out here on the left-hand side. We'll write it out as what we call a parent nucleus. Or if you want to think of it as a reactant, chemical terms, a reactant. This is what goes into the reaction. This is what we have before the reaction takes place. So radium-226. Where have you heard that element before? Radium. Where have you heard that word before? Radium. Yeah, the periodic table, sure. Yeah, the place, Radium, BC. And what are they famous for? Hot springs, natural hot springs. Why do they have hot springs? Natural hot springs. Why is this hot water all coming up from the ground? Why do you think it's called radium? Why do you think the town is called Radium? Because there's a lot of radioactive radium in the ground. And as it decays, it generates heat. And what does it do to the water, the groundwater? It makes it hot. And it comes up. And then what do? You go for a swim in the hot groundwater, right? That's why the town is called Radium, because that's what's underground in Radium, BC is radium. Now it undergoes alpha decay here. So we're going to say, put a little arrow there showing that radium-226 becomes something. Well, it undergoes alpha decay, so we know that it becomes an alpha particle. We could have wrote 4,2 alpha or 4,2 helium, either one, because they both mean the same thing. Remember what we said? We got to balance the nucleon number, that's the number on the top, and the atomic number, that's the number on the bottom. So let's say 4 plus 222 equals 226. We just balance the nucleon number. 2 plus 86 equals 88. So this radium decays into an alpha particle, and it also decays into, well, whatever 22686 is. Sorry, 22286 is. How are we going to find out what that is? Look up this number on the periodic table. All year you've been like, why do I have a periodic table in my data sheet for today? This is why you have a periodic table in your data sheet. I believe you'll find that number 86, atomic number 86, I think is radon, I believe, which is itself radioactive. So this wouldn't be done. There would be another reaction that would take place after this. But this is one step closer to being radioactive. You ever heard of radon gas? Yeah? Yeah. Like southern Alberta actually it has more radon gas naturally occurring in the ground than most places in the world. And it's actually a really big cancer causer. Like I think I've read that it's like second behind smoking in terms of causing lung cancer. And we got a lot of it in the ground in southern Alberta. You can hire people to come in and mitigate your basement to prevent radon gas from seeping in to your basement. A lot of people have done that. You get a test done to see if there's any radon gas seeping in. And if there is, then they can mitigate it by creating a negative pressure in your, like below your basement, to basically suck the radon gas out, and then it just dissipates in the air outside your house. The problem with radon gas is if it seeps into your basement, if you breathe that radon gas, and then it decays once it's in your body, right? Then it produces these ions that aren't supposed to be there, and strange things can happen. So radium-226 becomes an alpha particle, and radon-222. Make sense? Now, it wouldn't be necessarily done. Again, radon can decay it itself, but the problem that we're asked is done here. Okay, let's take a look at example number 2. Write the nuclear decay equation for the transmutation of lead-214 undergoing beta-negative decay. So we'll say 214-82 lead goes to 0 minus 1 beta. It produces a beta particle, a beta-negative particle. Or we could have said 0 minus 1e. It means the same thing. Plus what? Well, let's balance the nucleon number. 0 plus, well, that's easy. 0 plus 214 equals 214. Minus 1 plus what equals 82. The most common mistake that people make in this entire unit right now. Minus 1 plus what is equal to 82? What is it? 83. What do you think the common mistake is? What do you think people will often put here? 81. Yes, it's not 81. It's 83. And I believe that's bismuth, Bi, to check your periodic table. Bismuth. Now, there is also something else produced here. We call it an antineutrino. An antineutrino, just a little particle that accounts for some missing energy. It doesn't have any significant mass, so we don't have to worry about balancing or anything. Every time you have beta negative decay, you get an antineutrino produced. Every time. Number 3 says, write the nuclear decay equation for the transmutation of radioactive isotope magnesium-23 undergoing beta positive decay. So that's 0 plus 1 beta. Plus what? Well, 0 plus 23 equals 23. Plus 1 plus, what would this one be? 1 plus 11 gives me 12. What's atomic number 11? I don't remember, actually. Is it? It's not sodium, is it? No. Is it sodium? I don't remember the entire periodic table. I certainly don't expect you to remember the entire periodic table. That's why you have it given to you in your data sheet, right? Oh, plus what? What do you think is produced here? Sorry? Yes, not an antineutrino, but a neutrino. Notice the difference in symbol. An antineutrino has a little line over the top of it, and a neutrino just has the base symbol. These aren't too bad, are they? Yeah, these aren't too bad. Just a little bit of addition, subtraction. Well, then you got to remember the neutrino and antineutrino as well, I guess. But let's do one more, okay? Do one more, and then I'll shut it down. Example number 4. Oh, there's 3 parts to it. Serious? He says, yeah, let's do one more, and it's one more, ABC. That's okay. That'll go quick. Complete the following nuclear equations. All right. That's okay. It'll go quick for us. 3015 goes to 3016 plus, well, that would be 0 minus 1 beta, right? 16 plus minus 1 is 15. 30 plus 0 is 30. Plus an antineutrino, because it's beta negative decay. Okay, let's say 234 plus 4 gives me 238. 90 plus 2 gives me 92. That would be an alpha particle, right? Plus nothing. Nothing comes after alpha, right? There's no neutrino or antineutrino. Neutrino is beta positive. Antineutrino is beta negative. There's nothing after the alpha. The last one here, 13 plus, that would be 0 is 13. 6 plus 1 is 7. That would be a beta positive particle. What else do we got there? Neutrino. You know what? I lied. Let's do one more. To be honest, I was thinking this one was the next one that I was thinking of. It's just one more. It's just a tiny little twist on it. You could probably do it without my help, but just to make sure before I set you free to work on your worksheet. Okay, last one, I promise. You know what? I won't even make you do A and B. We'll just do A, okay? This is what we call an artificial transmutation equation. This is not natural radioactivity because, look, it's not nitrogen decaying into an alpha particle. It's nitrogen being bombarded with an alpha particle. It's the alpha particle hitting the nitrogen. So we're taking an alpha particle, we're firing it at the nitrogen. And that becomes oxygen 17. And then that oxygen 17 and something else as well. Well, what is the other thing that's produced here? We would say 14 plus 4 is 18. 17 plus 1 is 18. 14 plus 4 is 18. 17 plus 1 is 18. 7 plus 2 is 9. 8 plus 1 is 9. 1, 1, that's not a beta particle, beta negative or beta positive. That's not alpha. What's that? It's hydrogen. Yeah, check your periodic table. It's hydrogen. Or it would also be a proton, right? 1 plus 1, and then the top number is the number of protons and neutrons. So you could say 11H, or you could say 11P for protons. Either one of those would be fine. So that's not radioactivity. It's another type of transmutation. But we deal with it in the same way. terms of the analysis. I'm going to ask you to take a look at worksheet number 24. It looks long, 14 questions, but you can imagine how quickly each of these questions is going to go, right? All we're doing is adding and subtracting. So let's do all 14 of these questions, and we'll take a look at them tomorrow.